Section 3.4, solving systems of linear equations in three variables. So a solution to a system of three equations in three variables is going to be an ordered triple. And always make sure that you list these in alphabetical order the same way you would an ordered pair. And this ordered triple is, when it's substituted into the three original equations, it will be a solution to all three of those equations. Three variables represents a three-dimensional plane, so you can kind of think about what three equations and three variables would be if you think about the corner of a room where two walls and a ceiling come together. So where all those three come together is the point of intersection that we're trying to find when we find our ordered triple. So the hardest part about solving a system of equations in three variables is trying to remain organized. And the more you remain organized, if you understood linear combination or elimination of two equations with two variables, then three equations with three variables, if you're able to stay organized, shouldn't pose too many more difficulties. So the first thing I want to do is number our equations. So I'm going to number them 1, 2, and 3. And our first goal is to pick two equations and eliminate one of the variables. And then we're going to pick two different equations and eliminate the same variable. So we're ultimately going to end up with two equations with two variables. And so to begin with, I'm going to take equation 1, and if I take equation 1 and multiply it by -2, and I combine that with equation 3, then my y term will end up canceling out. So let's see what that looks like. If I take equation 1 and multiply everything in the equation by -2, then I get -4x plus 2y minus 12z equals 8. And then I'm just going to keep equation 3 as it is. And when I add those two equations together, my y terms cancel out. So I end up with this equation, which I'm going to number equation number 4. And now I need to eliminate the y term again. And so there's multiple ways you could do this. And I just happened to pick the y term, but we could have eliminated either of the other variables as well. But now I'm going to take equation 2, and I'm going to multiply equation 3 by a +2. And again, if I take equation 2, multiplying the third equation by a +2, and now if I add those two equations together, again I will eliminate the y's. And I'm going to name this equation my equation number 5. And so now if you think back to section 3.2, when we had two equations and two variables, I could solve this by substitution or linear combination again. So again, I'm going to take equation 4, and to me the easiest thing to do would be to multiply equation 5 by a -4. And if I do that, we will see that our x's will be the same coefficient but opposite, so that now when we add these together, we get -27z equals -27, and I've determined that z equals 1. Now I can take this and substitute it back into either one of equation 4 or 5, because I have an equation with x and z for both of those. And since I know what z is, I could find x. So I'm going to take equation 5 and plugging 1 in for z. And now if I go ahead and solve this for x, we'll see that we get x is a +3. Sorry, a -3. And now I'm going to take those and substitute it back again into any one of the original three equations. And I just happen to pick the first equation, substituting the -3 in for x and the 1 in for z. And when I solve this, the -6 and the +6 cancel, and I get y equals -4, so y equals 4. Now please don't make the mistake of leaving your answer like this. It's an ordered triple in alphabetical order. So listing the x, y, z, we've got -3, 4, and 1. And again, a great way to check your solution, this is one reason I've always liked algebra over some other math classes, is that I can take my -3, 4, and 1, and if I substitute it back into all three of my original equations and it comes out true, then it is indeed a solution to that system. All right, so let's try the next equation. Again, the first thing we need to do is number our equations, 1, 2, and 3, because it's a lot easier to keep things organized and to know which equations we've used if we number them. So if we look at this, we can see that if we take equation 1 and equation 3, we already have the same coefficient but opposite, again with our y's. So if I write both of those equations down and then add them together, my y's eliminate, and I get 3x plus 3z equals 9. And again, if I take, I could do various things. I chose to take equation 2 again, and I'm going to multiply the third equation by a positive 3, and again, my y's will eliminate, and I'm going to get 9x plus 9z equals 29. And again, I'm going to number these equations 4 and 5. And now I need to eliminate either the x or the z. Going back again, thinking about section 3.2. So if I multiply equation 4 by a negative 3, and then I keep equation 5, I can see that I'm going to get 0 on the left-hand side, because coincidentally my x and my z will eliminate. I'm going to get 0, but negative 27 plus 29 is 2. This obviously is not true, so you should be aware that this is no solution. These three lines, or planes actually, do not intersect at all. And now a third example. Again, number the equations. And again, if I look at this, it really is totally coincidentally that on all these examples that I've done so far, I'm eliminating the y. We really could pick any variable. But again, if I take equation 1 and 2, I can see that my y's are already the same but opposite coefficients. And so now when I add these together, I'm going to get 2x plus 2z equals 12. And again, I can take equation 2 and 3, because again, my y's are the same but opposite. And so if I write those down and I don't have to multiply either equation by anything, I'm going to get 5x plus 5z equals 30. Again, numbering these other two equations, and now I need to eliminate the x or the z. So if I take equation 4 and multiply it by 5, and I take equation 5 and multiply it by a negative 2, well again, when I write these out, you'll be able to see that everything cancels, so you get 0 equals 0. And since this is true, you should know that the answer will be infinitely many solutions. And now let's try a word problem. At a carry-out pizza place, an order of 3 slices of pizza, 2 breadsticks, and 2 pop cost $13.35. An order of 5 slices of pizza, 2 breadsticks, and 3 pop cost $19.50. And an order of 4 breadsticks and a pop costs 30 cents more than a slice of pizza. What is the cost of each item? Well, this is a word problem, so the first thing we need to do is define our variables. And we look to figure out how to define our variables by looking at the question. The question is asking what is the cost of each item. Therefore, I'm going to let x, y, and z be the price of the pizza, the price of the breadsticks, and the price of the pop. And now we need to come up with our equation. Well, again, using the idea that we have a number of how many things we ordered and the price, we're going to use our familiar model of price times the number. So if I look at this, we have 3 slices of pizza, 4 breadsticks, and 2 pop, costing $13.35. So again, price times the number, 3 slices of pizza times the price of the pizza, which is x, plus 4 breadsticks times the price of the breadsticks, which is y, plus 2 pop times the price of the pop, which is z, gives us the total amount we're spending. My second equation we're going to come up with similarly. I have 5 slices of pizza, 2 breadsticks, and 3 pop for $19.50. So again, price times the number for each item equals $19.50. The last equation shouldn't be too tricky, but we have an order of 4 breadsticks and a pop. So we can write that as 4 breadsticks and 1 pop. That's the price times the number again. And that costs, well, cost is the same as is, so that's what our equals is. And then 30 cents more than is going to be 30 cents added onto the price of a pizza, so the slice of a pizza. And now, just to make this a little bit easier to deal with, we're going to get the x, y, and z all on the same side of the equation, and so we can eliminate that equation that we used to write our system with negative x plus 4y plus z equals 30 cents. Again, numbering our equations, and again, we would need to eliminate one of our variables. Well, since I see that the third equation has a negative x, I am going to take equation 1 and 3, but I'm going to multiply the third equation by 3, and this will eliminate our x's. So the first equation remains the same. The third equation, I'm multiplying everything by 3, and when I add those together, I get 16y plus 5z equals 1425. Again, we need to eliminate the x, so again, I'm going to use equation 3, but this time I'm going to pair it with equation 2, and I need to multiply it by 5. And so that's what I get when I multiply the third equation by 5. And adding those equations together, I get 22y plus 8z equals 21. Numbering those equations, and now I need to eliminate either the y or the z. Well, simply because I like to keep my numbers smaller, I'm going to eliminate the z. I'm going to multiply equation 4 by 8, and I'm going to multiply equation 5 by negative 5, and this will get the coefficients of my z to be the same but opposite. And so now again, when I add these two equations together, I'm going to get 18y equals 9. And keeping in mind that we're dealing with money, it wouldn't be as appropriate, I guess, to write it as 1/2. So I'm going to write it as a decimal because then we're dealing with money. That would be 50 cents. And again, I'm going to take that and substitute it into either equation 4 or 5, to figure out what z is. And when I solve this, I find that z is 1.25. And then taking my y and my z and plugging it up into any one of my original equations, I chose example 3, or equation 3, to solve for x, and I find that x is 295. Now again, make sure you're aware that this is a word problem, so I need your answer to the question. The cost of each item. Pizza cost $2.95, that was my x. Breadsticks cost 50 cents, and I don't care whether you write it as $1 with a decimal of 50 cents or 50 cents with the cent sign. And z, my pop, cost $1.25. And I have one last problem to do, and rather than talk you through this, I am going to just do the problem, but I would encourage you to pause the video and attempt to do this problem on your own, and then possibly play it and pause it to make sure that you got each of the steps right. But I am not going to talk you through this last example, so if you have any questions, this would be a really good problem to make those notes as far as what I was doing for each step. Numbering the problems is the first step, and now we'll go ahead and solve this system of equations. Keeping in mind that if you do pause the video and do it on your own, if you start off eliminating a different variable than I did, then we should still end up with the same answer. So there's more than one way to approach a problem. So don't erase what you've done if you come up with the wrong answer. Bring it to class so we can all work through it. And so my solution is 1, 3, negative 2. And hopefully either yours is, or you'll come to class with your work still there so we can figure out what mistake you might have made. Again, please make sure you come with any questions to class. And again, don't forget to go back and do the notes check. And we'll see you tomorrow.